Hello.
Hi, Adam.
How are you?
I'm fine, thank you. How are you?
I'm good.
We're just finishing setting up the live stream. And that is running now.
The weather looks very nice there on Mount Olympus.
Oh, am I still on La Palma? Yeah, I guess
Yeah.
so.
How are you?
I'm fine, thank you. How are you?
Good.
Just finishing setting up the live stream. Now. Okay. Live stream is running. So I'm just going to wait a couple more minutes.
Yeah, it looks like people are still joining.
Yeah, I have a few words to say just about the setup and make a quick announcement, and then I'm going to hand it over to you at 9 a.m. your time. So from La Palma to the Hubble Deep Field.
Distance and time.
Yes. How do you breathe in there?
We bring our own oxygen. Vivian Poulin says he has no microphone now. Hopefully he can do sign language.
All right, I guess it's 2:50 local time. So that means we're off to a go. Dear colleagues and participants, welcome to the ESO H0 2020 e-conference. We're really excited to start this week of amazing talks and stimulating discussions. Firstly, I would like to thank all of you for joining us today. For the duration of this short introduction, why don't we all turn on our videos so that we can all see each other for a few minutes. Please do keep your mics muted. Eventually, we will want to turn off the videos again to make sure that we have a smooth video call, but it's just nice to have that in-person interaction that we don't otherwise get. So hi to everyone. This e-conference, as you may realize, is a bit of an experiment, and we realize that the timing of this global live event is not exactly comfortable for those joining from regions bordering the Pacific Ocean. So thank you all really for making this experiment possible. And a very warm thank you also to the other organizers, Sherry Suyu and Antoine Méran, as well as our local admin assistant, Stella, and to lots of other people who helped by discussing and encouraging us to pursue this and by contributing ideas. We're very happy to share that you share our enthusiasm to keep scientific discourse alive, even while the world is in lockdown due to extraordinary circumstances. Our thoughts are with all those who have been negatively impacted by the COVID-19 pandemic. We realize that this is a tough time for many people, and we hope that this conference may serve also as a source of motivation and inspiration to keep spirits high in times of distress or difficulty. For those of you who followed the progression of our planning, you will recall that this conference was originally planned as an in-person meeting to be held at ESO headquarters in Garching, Germany this week. To make the most of our existing plan and schedule, we decided to convert our in-person meeting to an e-conference, and we worked hard to try and make this meeting effective, inclusive, and interesting. Based on our onboarding survey, we understand that approximately half of you might not have attended this meeting in Garching, and we take this as a sign that the lack of travel and the free registration helped reduce barriers for some of you. Of course, we are also aware and glad that the carbon footprint of this conference will be significantly lower than that of a traditional meeting. We see e-conferencing as a useful tool for reducing the ecological footprint of scientific activities and for increasing diversity. Following this conference, we plan to issue a report on the do's and don'ts of e-conferencing. Please fill in our onboarding and post-conference survey to help us develop these opportunities for the future. Moving a real-world conference to the virtual domain meant that some things were done differently compared to if we had planned this as an online event from the start. The most notable effect was that we unfortunately could not offer contributed speaker slots while keeping the impressive set of speakers that had previously accepted our invitation. To nonetheless enable lively discussions, we have included half-hour discussion panels at the end of each day, and we have set up a Slack workspace for exchanging thoughts and ideas throughout the week. We hope 30 minutes will be enough to get a good discussion going. Due to the many time zones involved in the conference, we will ask the panel to migrate discussions to Slack should the 30-minute window prove to be too short. During the panel discussions, we will ask all of today's speakers and the panelists to turn on their video. All non-panelists, please keep your videos off and your mics muted. Thank you. Before we get started with science, I would like to make some technical announcements and reminders. First, please use Slido for all questions. Links to Slido are publicly available on the conference program webpage. There is one link for each talk or panel, and this allows everyone to participate at the same level, even those on YouTube. Please use Slack for all discussions. Registered participants have received invitations to join our Slack workspace. If you need us to resend the invitation, please email us. Please do not use the Zoom chat for discussions or questions. We have Slido and Slack for that. Unregistered participants are also welcome to use the YouTube live chat and leave comments there. We will do our best to follow these developments, but Slido and Slack are the most useful platforms for questions and discussions. Please review the descriptions on the conference website if you have any questions about the setup. There is also a short 5-minute video that explains it. So much for the technical things. Now to why we're all here. Sharing the screen. As we all know, the value of Hubble's constant has recently been shown to be in significant discord between the early and the late universe measurements. Almost exactly a year ago, a conference at KITP summarized the findings using this plot. Hubble's constant has thus become the most discrepant, though not the only, cosmological observable, suggesting that some unknown physics may be hidden or at play. However, there's not yet a very clear theoretical explanation for this discord. Moreover, as we're entering the era of extremely precise H0 measurements, previously overlooked systematics start to become more and more relevant. At the same time, there's so many different subjects and areas of expertise required to understand what's going on that it's really a challenge to follow all of these various arenas at the same time. Therefore, we have designed this e-conference to provide a bird's eye perspective of the various connected issues to assess the uncertainties in Hubble's constant, as well as its implications. Over the course of this week, we will take stock of the latest measurements and assess how the field has progressed during the last year while focusing our attention on uncertainties. We therefore invite all of you to share in the discussions on what needs to be done and where we may progress. This will help us understand where progress is possible and where research efforts should be directed. So now, without any further ado, let's get started. Adam Rees will now present the latest results of the SHOES team. Adam, please go ahead and share your screen. Everyone else, please now turn off your videos and make sure that all the mics are switched off.
Okay, can you see my screen?
Yes, sir.
All right, very good. Well, normally I say thank you for inviting me here, but I'm just here at home. Nevertheless, I will look forward to having a nice German beer at the end of the day to celebrate the first day of conference. I will be telling you about recent progress in measuring the late universe value of the Hubble constant from the SHOES team, what we're finding, and the efforts we're making to approach a 1% accuracy in this measurement. And I identify below a couple of recent reviews and a paper if you want to dig into some greater details. Now, since this is the first talk of the conference, I thought I should give a little bit of introduction to the problem. Oops, there we go. So after about a century of cosmological research, we have realized a standard model of cosmology, lambda CDM, that is very powerful. It has 6 free parameters and a number of ansatz, though embarrassingly, 95% of it is still in the form of dark components whose nature we don't deeply understand. However, we make simplistic assumptions about those dark components, and then we use this form of the model on the left as it would have looked before recombination to predict the physical size of fluctuations in the early universe, including the sound horizon and also the baryon density. We then observe those early relics in the universe, the angular fluctuations from the cosmic microwave background, or we can measure the deuterium abundance for the primordial abundance. We then compare those relics to the model predictions, and in that step, we have effectively calibrated the free parameters of lambda CDM. We then use the evolving form of the model throughout cosmic history to predict the expansion history of the universe all the way to the present time. We get a couple of tests along the way. For example, high redshift supernovae and baryon acoustic oscillations act sort of like guardrails. They check some of the curves in the road, like the acceleration from dark energy, but they don't tell us that we have overall the right model. And finally, this chain from early measurement to model leads to a prediction of the Hubble constant of 67.4 plus or minus 0.5, just using the most precise from the Planck Observatory. And so a powerful end-to-end test of this whole story, including the uncertain parts, is to make a direct measurement of the Hubble constant to comparable precision. So about 15 years ago, my colleagues and I started a project called the SHOES project to do just that, to reach a percent level precision measurement empirically using geometry to calibrate pulsating stars, Cepheid variables, to calibrate exploding stars, type 1a supernovae. Now, we have a number of unique assets at this point in our approach. We have reduced the systematics in all of our Cepheid measurements by using a single telescope for all of those objects, and by making those measurements in the near infrared, where dust and the effects of metallicity are greatly mitigated. We have the most independent geometric calibrations of our ladder. I'll say more about that in a minute, and the largest set of homogeneous type 1a supernovae. And this has been driven through 17 competed geo proposals, more than 1,000 orbits of HST time. So it has been quite a significant investment. So where we are today, or as of a few months ago, the data more or less looks like what you see, sort of nested 3 rungs. In the first rung, 5 independent geometric sources are used to calibrate the luminosity of Cepheid variables. In the intermediate panel, we use the Hubble Space Telescope to observe those Cepheid variables in the hosts of 19 recent type 1a supernovae to calibrate them. And then in the last panel, a few hundred type 1a supernovae and their distances calibrates redshift, and we get 73.5 plus or minus 1.4, a total uncertainty of 1.9%, and of course a strong tension already with the Planck measurements plus lambda CDM, about 4.2 sigma. So let me update the status a little bit. What makes this problem so interesting or exciting, I think, is, as Richard described in the beginning, the recent updates. Last year, we had this big conference at KITP where many sort of late-breaking results were presented by different teams. And what materialized, as you see, is a result, a tension that does not appear to depend on the use of any one method, team, or source, as we described in that review article. And just to put a finer point on that, we literally mean you could remove any one of the following: Cepheids, tip of the red giant branch, lensing, type 1a supernovae, Planck, or the CMB, and you're basically left with a kind of a tension, or we argued a lot, or was it a discrepancy or a problem, but somewhere between 4 and 6 sigma that looked quite profound. And with, I would say, a little bit of deja vu from last year, just weeks before this conference, a number of new results have come out which continue to reinforce this discrepancy. Just last week, two new measurements from the Tully-Fisher method, either the infrared Tully-Fisher or the baryonic Tully-Fisher calibrated by tip of the red giant branch or Cepheids, came out and continue to reinforce this. In fact, let me just briefly review a number of new breaking results just in the last couple of weeks. One that I was very excited about was the availability of 2 new geometric anchors for Cepheids. These were measured by Luisa Bruval and her team of collaborators using Gaia DR2 parallaxes of binaries in Cepheids in binaries using the companions, or alternatively using the clusters, which is both new approaches. I mentioned the infrared and baryonic Tully-Fisher results. There was also a new paper standardizing type 2 supernovae instead of type 1 using Cepheids and tip of the red giant branch. All of these reinforcing or growing the evidence that we see, as well as a little further back, the STRIDES team's double lens system. There's been a lot of activity trying to understand the reddening in the LMC and how that can impact the TRGB calibration in H0, as that's the primary calibrator, using RC stars versus tip of the red giant branch colors. I list a bunch of papers that have gone back and forth on this. I'm happy to take a question about this during Q&A if people want to ask more. And then, not to forget the early side, another result reinforcing that tension, the galaxy power spectra shape measurements combining BBN, again, early universe physics, giving the now fairly standard low value. So for the rest of this talk, I'm going to focus on our approach using Cepheids and type 1a supernovae. And I just want to say, explain why is it that we've focused on Cepheids so much? Well, they really are the longest range distance indicator for stars. And so they bring the largest sample of supernovae in play. They're also they have the most independent calibrations. It's possible to measure their photometry consistently along the whole ladder. But I think the most important feature is just that they're most tested by the community. Culling out, in the last 20 years, there have been numerous publications using Cepheids and type 1a supernovae, but with a wide range of HST instruments done with different teams measuring their own photometry at different wavelengths. There's been reanalyses of our shoes team data, even by Planck people, and using different sets of supernovae or completely different styles of analysis, Bayesian, hierarchical. There's been graduate student problem sets assigned to do this. And the results are very consistently in this range of sort of 71 to 76, sort of very much in keeping. And so at this point, it's very robust to analysis. You can go through the now 7 different geometric anchors of the Cepheids, the masers, the detached eclipsing binaries, various parallax measurements made with different instruments or with Gaia, but different kinds of companions. And these are all giving very consistent results. In addition, we go through all kinds of analysis variants. There was a question just before from Benham about how the reddening, it's very mild, but the reddening in the near infrared affects the Hubble constant. So we show here different reddening laws, different values of the reddening term, which have very little impact, or one could ignore reddening altogether since we are making observations in the near infrared and it makes little difference. Likewise, variants of the slope of the period luminosity relationship have very little impact. So I'm going to now launch into the efforts to control systematics at the 1% level for Cepheids and type 1a supernovae. So the typical systematics we worry about, like reddening, we think we already have well in hand due to the use of the near infrared measurements and the use of Vezin height magnitudes. Metallicity dependence, we have 3 approaches to this, which is to calibrate the metallicities locally with spectra and regress out any dependence, as well as make the measurements in the near infrared where the dependence is much weaker, and to make our measurements over a narrow range of pretty metal-rich metallicity so that there's very little lever arm for the effect. For photometry calibration, which used to be very challenging, use of the same telescope for the Cepheids and anchors to hosts checks that box. For analysis, going from just the raw photometry to the Hubble constant. Here, we've really relied on the community. We've made our photometry public, and the community has scooped up all that photometry and reanalyzed it so many ways. We've really learned about the robustness, as I said, from the community's reanalysis. Now, let me talk about 2 new systematics here. One would be Cepheid selection, how different people or pipelines would select a sample of Cepheids. We've done tests of this most recently, comparing an automated pipeline which we built and compared that to the manual selection of Cepheids. And what we found for a very large set is about 93% overlap in terms of which Cepheids are selected. And the net effect on all the periods translated to magnitudes is just 3 millimags in the mean. So the selection doesn't seem to have any significant impact. A good manual example comes from NGC 3370, where it's literally been analyzed from scratch 3 times by different people, Peter Stetson, Lucas Macri, and Samantha Hoffman, with differences in log period that were negligible and in magnitude of about 0.01 magnitude. Just to say, in terms of the random error on the periods in log period, the random error is about 0.01 magnitudes, which maps to 0.03 magnitudes in the PL relation. And so that's the smallest form of uncertainty that we see. Okay, for the rest of this talk, I want to talk about what has in the past been considered the most tricky systematic for Cepheids, which is crowding. It's not just me saying this. I quote from a recent paper last year by Wendy Friedman and collaborators, who point out, rightfully so, that this is possibly the most significant challenge for Cepheid measurements beyond 20 megaparsecs, crowding and blending from redder disk stars, particularly in the near infrared, where, of course, the effect will be larger because of the lower resolution. And so here's basically a setup of the problem. In an ideal scene that you see on the left, the Cepheid is nicely in its resolution element all by itself, and you can measure its photometry very well. In a real scene, the scene is sprinkled with field stars and other things, and those can blend into the resolution element and would make the Cepheid appear brighter if you didn't recognize the presence of such stars. Of course, you can see the presence of such stars in the annulus around the Cepheid, and so therefore the conventional the conventional approach would be, and always has been for maybe 20 years, to inject artificial stars into the annulus of known brightness and to measure the effect of crowding on those stars and correct the Cepheid for that. Now, this is a good approach, but it's indirect. It's not at the position of the Cepheid. It's assuming that regions around the Cepheid are just like that position. But we have recently analyzed and published a new result that provides a very powerful direct measure of crowding. And it looks like this, more or less. When you blend some static flux in with a variable source like a Cepheid, not only will the combination appear brighter, but it will change the light curve of the Cepheid. When the Cepheid is at its faintest, the contributed flux will have a bigger fractional impact than when the Cepheid is at its brightest. And so therefore, if you look at the light curve in fractional flux, or what astronomers like to call magnitudes, then you will see in the case of crowding, the light curve's amplitude will be compressed. And so this is a direct consequence, a direct signature of crowding. And there's a very simple mathematical relation, which we derive in the paper, that the observed amplitude that you see will be smaller than the true uncrowded amplitude by just a simple function of the amount of crowding, giving you a very simple way by measuring the amplitudes to directly measure the crowding. And there's no free parameters in this. So just to show you 3 examples to illustrate this, in a galaxy at 20 megaparsecs, NGC 1559, here's a Cepheid way far out where there's very little local crowding, and you could see indeed in its near infrared light curve, it has the full expected amplitude we see for Milky Way Cepheids. The optical light curves in black all suffer very little crowding. Then if you go further in where there is some crowding, now you see the compression of the near infrared amplitude. If you go very deep into the galaxy where crowding is extreme, and I will say we don't measure H0 this far in, but it's useful for illustrative purposes, you can see the amplitude can be compressed altogether. So this is a very powerful diagnostic of the crowding directly. And so we've measured now the amplitudes of 225 extragalactic Cepheids in the near infrared, and we've compared those to their Milky Way counterparts as a function of the local crowding we see around each Cepheid. And so what we see is that the data, and in red is the binned data, follows exactly the prediction, which has no free parameters, shown here in black, or if you just did a free form fit, a second order fit in blue, those agree very well. So the measurement of crowding done locally, indirectly with artificial stars, is exactly predicting the changes in amplitudes that is directly from crowding. So for example, where you have no crowding, far out in a galaxy, the extragalactic Cepheids have amplitudes that match. The ratio is 1 to their Milky Way counterparts. When you go very far out where the crowding is high, then the amplitudes are suppressed, but exactly by the amount that the crowding locally predicts. So this really confirms the accuracy of crowding measurements that people have been using for, as I said, about 2 decades. In fact, you can turn the problem around and say, well, how much additional or unrecognized crowding could there be? And so you form a chi-square statistic to compare the amplitudes of Milky Way Cepheids to those in distant galaxies, allowing for additional unrecognized crowding. And you constrain that term, and it's consistent with 0. And in fact, the uncertainty in that is less than what is 1/5 of the tension in the Hubble constant. Or in other words, we can really rule out 2/10 of a magnitude of unrecognized crowding. That's the amount needed to explain the Hubble constant at 5 sigma. This in addition to other more indirect tests of crowding I list below. So finally, I'm often asked the question, could we live in a giant void causing this? 9% in the Hubble constant. And if you look at, and I think we'll get into this later, large scale structure theory and body simulations, but also the Hubble diagram of type 1a supernovae, these both allow you to measure that the variance from this structure would be about 0.6% in H0. So really inconsistent at 15 to 20 sigma with that deep a void. Is the flux scale of HST really linear to 1%? And yes, I would say it's recently been calibrated so that this contributes about 0.3% uncertainty in the Hubble constant across 15 magnitudes. Is there a difference in the supernovae themselves at the two ends of the distance ladder? And I would say not in any significant way. We've looked at correlations of Hubble residuals with environmental parameters. Most of those are insignificant. The ones that are modestly significant could argue for a 0.3% in H0 shift, but that's not very much. Going forward, we will be using complete samples in redshift of matched hosts to avoid even the possibility of this arising. So looking forward, over the next few cycles, we are going to be collecting 24 more Cepheid supernova calibrators to go from 19 to 43. We also expect to be observing Cepheids in coma directly to actually skip supernovae altogether to provide another test. Here's what the data looks like. I have to have it zip by very fast because it's still preliminary. And so in the next couple of rounds, I expect to see the uncertainties go down to about 1.2% as we double the supernova calibrator sample, increase the sample of nearby supernovae, hopefully make use of a Gaia DR3 release. And we also look forward to ongoing tests from, as I said, 2-rung distance ladders without supernovae, LIGO, the use of other high redshift measurements that can better constrain W of Z, which helps either demonstrate that late dark energy is a problem or eliminates late dark energy altogether, as well as new signatures in the CMB. So I'll close here with just a few final thoughts on this. The discrepancy that we see between the early and late universe Hubble constant depends on which combination of measurements you use. Could be anywhere from 4 to 6 sigma, probably typically about 5 sigma. So I think it's very significant. I would say we see no late universe measurement that is lower than any early universe measurement. That is significant. It appears to be very robust because it would require multiple catastrophic failures to avoid. I think people who attribute it simply to systematics have maybe not internalized this update in the last year or so, that so many independent measurements have come to this conclusion. So therefore, I think it's very interesting, unless I would say your Bayesian prior on vanilla lambda CDM was already much higher than 5 sigma. Why is this going on? Well, I only have a 20-minute talk, so I couldn't get into that, but I'll leave that to Lloyd Knox's talk. From my perspective, I would say I feign no hypothesis. I think we just need to follow the evidence. And remember, even when we're looking at theoretical solutions, even if none of them are the right one, it may be the case that the universe is more clever than we are now, and a better idea will come along later. So I will end there, and thank you.
Thanks, Adam. Applause for Gaji. So before we go into questions, I would just like to briefly share my screen just to show everyone how Slido works, and basically give a quick view of this system. So on Slido, via our conference website, you have a link to each talk that has a specific Q&A link provided. If you click on this, it'll take you to a question page like this, where you can type in your question together with your name or anonymously, and you can type a 160-character question, which will then show up in this listing, and people can upvote relevant questions. So by voting for questions, we can all decide which ones are the most relevant to ask. It's best to do this early on during the talk. That way you can gather votes for your questions, and that way it makes life easy for me, so I can just skim the best questions from the top and ask that directly to the speaker. So I will stop sharing my screen and hand it back over to Adam and just ask you questions directly. The first one comes by Matthew Collis, which is, what is the ultimate systematic floor for distance ladder, Cepheid and type 1a supernovae, H0 precision? When will that be achieved?
Let's see. So what starts to happen as you chew on various errors and come up with ways to measure them is, you get the biggest ones to come down, but eventually at the end, you're stuck with this kind of sea of a broad range that are all about a fairly comparable level. So the end result won't be 1% systematic error and everything else 0.1%. It's going to be a whole bunch of things that are going to be more like a third, a half. But I would say that cosmic variance one is starting to really, become a rate limiting step. I mean, we're looking at that very carefully, but 0.6%, in some ways I've seen people do this. It could be 0.7%. That's not something that we're going to be easily able to reduce. And then that, combined with other things is probably going to dominate our 1% error. In fact, I can't even promise we'll get to 1%. I mean, I'm being kind of optimistic that everything clicks together to get to 1.2%. One of those things is Gaia DR3. Gaia DR3 has had some systematics that I hope they tackle DR2 had some systematics that I hope they tackle in DR3. If they don't, then we may not get to that 1.2%, or it may require multiple methods to really average together to get there. But I'm optimistic that we have, between us and the community, enough precision now to see robustly that there is something different between the late and early universe results. Greater precision at this point may help us pinpoint the cause of it.
Perfect. Thank you. Lloyd Knox has a question. Can you say more about potential biases due to varying mix with Z of early versus late type supernova hosts?
Yeah, I think I have a slide about this. Let me just go back a little, sorry. Yeah, so we, in our initial analysis, we used all types of hosts, and that gives us this, that gives us that, that gives us this 73.5, but we also tried variants where we make all the hosts be spiral types, because after all, the ones that host Cepheids are spiral types. So we made all the Hubble flow ones. It has very small impact. We also did a variant where all the hosts are locally star forming ones. So from what we see, it looks like it can change the Hubble constant by a few tenths. Going forward, we're only going to use the same types of hosts at both ends, because if you don't, there is the potential to produce a systematic, whether there actually is one or not. And so we think that's the safest thing. So going forward in our next sample, our calibrator sample will be all of the type 1a supernovae that went off in late type galaxies within redshift 0.01. Those will be our Cepheid calibrators. And our Hubble flow will be all the type 1a supernovae that went off in late type galaxies to redshift 0.15. And in that way, nature shouldn't know anything different is going on inside 0.01 than 0.15.
Okay. Maybe one more question. I remind people everyone can continue submitting questions, and we can bring that up again during the discussion panel if we run out of questions during this Q&A. The next question is by Wendy Friedman, who has a question about what is the most distant galaxy for which you have done the crowding tests? Have you looked beyond 20 megaparsec where most of your supernova calibrators lie?
Oh yeah, now I'm a little unclear. The crowding, the artificial star test crowding tests we do for all of the hosts. So that goes all the way out to a distance modulus of 33.2, which is I think about 45 or 50 megaparsecs. The ones where we have done this new amplitude work are ones that we were fortuitously observing for MIRAs. And of course, MIRAs are ones you tend to do a little bit closer. So those ones we've done to maybe 25 megaparsecs, but we have a lot of our type 1a supernova hosts, including our overall supernova signal. I mean, if we had limited our Hubble constant measurements to within 25 megaparsecs, it doesn't change the precision that much, root 2, but not that much. And then of course, I think another very powerful test of crowding has been the use of NGC 4258 as an anchor, because it has similar crowding as supernova hosts. And so really the crowding effect more or less cancels there. So at this point, I think this, I don't know how tender we like our dead horse, but this one's been beaten pretty tenderly.
All right, perfect. Thanks very much, Adam. Thanks again from Gashi. Next up is Rachel Beaton, who will tell us about the Chicago Carnegie Hubble project. Rachel, are you there?
Yes.
Perfect. So you're welcome to start sharing your screen.
Oh, I need Adam to unshare.
I thought, okay, I'll try. There we
It
go.
says you cannot while the other participant.
You got it?
Yeah, I think so. Can everyone? Well, okay,
Yeah, we can
great.
see
We
you.
got some slides. All right. So hi, my name is Rachel Beaton, and I'm here to represent the Carnegie Chicago Hubble program. And we're working on a Cepheid independent path to the Hubble constant. Oops, let's see. There we go. So when it comes to putting Adam's work in context with what I'm going to talk about, it's important to realize that we have 3 steps, just like Adam. We do a geometric anchor. We then calibrate the supernova 1A, and then we use supernova 1A in the Hubble flow to ultimately get the Hubble constant. And no matter how many different ways you try to compare our methods, there will be some commonalities. We only have so many local supernova 1A. We only have so many supernova 1A in the Hubble flow. We only have so many geometric anchors. But what this path, so while we may share those aspects of systematics, I'm going to try to keep my talk focused on the things that we don't share to help everyone who's listening try to put our works into context with each other. So our measurement came out last year. This is our first full end-to-end H0 in Friedman et al. 2019. And we used the detached eclipsing binaries in the LMC to calibrate. We had 18 supernova 1A hosts to calibrate the supernova 1A. And then we used about 100 supernova in the Carnegie Supernova Project sample. And our result was a little surprising in the sense that we came out dead in the middle between the Cepheid-based calibrations and the most recent Planck measurements. So we're within 2 sigma of both results, which we didn't necessarily expect, but that's where we are. And there were hints at this from the previous work on the tip of the red giant branch, which was from In-Sung Jang's thesis. And we have done an end-to-end very tight analysis trying to control for all systematics. So before we use a distance indicator called the tip of the red giant branch. And so to talk about uncertainties in the tip of the red giant branch, I first need to explain how the tip of the red giant branch works. So how does it work? So first of all, we make color magnitude diagrams where here on the x-axis is the luminosity of the star. And on the x-axis is the color, which is basically the spectral index or the shape of the spectrum of the stars. And so this should look fairly familiar from Astro 101. Here at the bottom is the main sequence turnoff. So stars live on the main sequence most of their life. When they exhaust the hydrogen in their core, they turn off the main sequence and evolve off. That's what we mean. They come off the main sequence. This stretch here is the red giant branch, and the star becomes more luminous as it burns a hydrogen shell around an inert helium core. And so it evolves up this branch. And when it reaches the tip, which is the end of the RGB phase, that helium core undergoes something called the star undergoes the helium flash, which lifts the degeneracy that had been held in the core, that had been keeping the core together. And after this, the stars evolve very, very rapidly, which leave this sharp transition at the edge of the red giant branch sequence. So when we say tip of the red giant branch, this is what we're looking for. So some important points about the tip of the red giant branch is that we measure it statistically based on the end of a sequence in a color magnitude diagram. Red giant stars are really quite ubiquitous and found throughout all galaxies. So in all different components of galaxies and in all different sizes of galaxies. And the red giant stars themselves are intrinsically low mass stars. These are not massive stars, they're low mass stars. Another really important point to make is that this data that I'm showing you is actually from NGC 185. And the pointing that I'm showing you is actually from 4.4 RE from the center of NGC 185. So we're way out away from the central part of this galaxy with this data. And we can measure the tip of the red giant branch out away from the crowded and more complicated parts of galaxies. So I can add some more important points about the tip of the red giant branch, that we can use it in low stellar density environments, and we can use it in less complicated environments. Out this far away from galaxies, there's not as much gas or dust that we have to worry about. And the stars in these environments, so far away from the main body of the galaxy, are usually old and metal poor. And so the Carnegie Chicago Hubble program really uses the TRGB in the way that I just described to eliminate systematics and also minimize the systematics that we still have. So I want to show you how we do this in practice. So I'm going to show on one side here the IC 1613, which is a nearby dwarf galaxy. It's low metallicity. It's basically see-through. You can see all the galaxies behind it. And a higher metallicity galaxy, NGC 1365, which is a higher mass galaxy spiral. And this is really showing you the two ends of the spectrum and how similar our measurements are because we work out in the halo. So now you're seeing a color magnitude diagram again, and this is more realistic of how we measure these distances. We only get the top magnitude or two of the red giant branch, but for IC 1613, hopefully you can see how sharp the tip of the red giant branch is defined there. You could actually plot a ruler here and get a reasonable measurement of where the tip is with just drawing a line across this plot. When we go out to NGC 1365, it's not as obvious because we have different uncertainties here and there's more going on in the field, but you can still see that truncation right there. So the question is, how do we measure this? We actually just bin up and count the stars on the red giant branch in small magnitude bins. And you can see here, it's called a luminosity function. You can see in this middle panel how sharp that definition is where you jump up. And if you take the first derivative of that luminosity function, you actually get a sharp spike, which tells us where that jump is. Now we can apply this to a more distant galaxy and it's less obvious, but you can see the luminosity function here, and we apply the same techniques and we get a spike that corresponds to the tip of the red giant branch. And that's it. We've measured our distance. We don't actually have to consider much else in this formulation. So we determine our uncertainties using injection tests of artificial RGBs at the image level. It goes through our entire analysis, and then we run experiments to help get us our uncertainties, and we get both systematic and statistical constraints. But we're here to talk mostly about uncertainties, so let's jump into the game about uncertainties. So our geometric anchor right now is only tied to the Large Magellanic Cloud, so that's for 2019 and 2020. And so here's the color magnitude diagram again. There's that RGB of the Large Magellanic Cloud. You apply the same thing, the same techniques, and you get this nice sharp edge. So we can combine that with the detached eclipsing binary based distance, which will be talked about in a later talk. We do a small adjustment from ground to HST filters, and then you have to worry about extinction. And so as Adam pointed out, there's a lot of papers about extinction. And I think that just tells us that we have that stars are interesting and extinction is hard. So in lieu of spending a lot of time on this particular topic, I'm actually going to show you new work that we hoped would be ready in time, but 2020 had different things in store for us, where we've actually been working really, really hard on NGC 4258. So let's move away from the LMC and let's ask the question, do we get a similar calibration of the tip? So we measure, so this is actually data from Zheng and Li, 2017, which is what I'm going to show. And you measure the tip at about 25.37 mags. You can use the megamaser distance that was published in Read It All 2019, which will also be talked about in a later work. The extinction to this field is this is the Milky Way extinction, is very low. It's actually so small that it's statistically, in the original maps, it's statistically consistent with 0, which is why we take such a large systematic uncertainty. And lots of other tests that we're running in this forthcoming work led by In-Sung Zhang. And we get a calibration that is spot on with what we got in the LMC, which is minus 4.06. These are preliminary and conservative uncertainties. So you might be wondering, what about some of the other calibrations that have been published? In particular, Read It All 2019 actually did a calibration. And this starts to get into the fun uncertainties game. So this is NGC 4258. Here's this beautiful data from the SDSS. This blue field is the Zhang and Li field. And this red field is from a paper by Macri et al. In 2006. And here is the same field overlaid on a Galex image. So now we're seeing star formation and also on the H1 density. And so this field, this inner field sits still in the H1 disk of NGC 4258, even though it's very far away on the major axis from the center. And you can actually compare these color magnitude diagrams. So these data are processed identically using our CCHP pipeline. So here's the red giant branch for that outer halo field, and here is the outer disk field. Now you're probably looking at that and saying, okay, those look relatively similar, but so I'm going to draw your eye. So this line is roughly, this vertical line is roughly in the same place in both diagrams. And this horizontal line is trying to draw the blue edge of the tip is right here. So that blue edge is the edge you need to use, or the part of the red giant branch you need to use for this work. And if we look over into the outer disk field, we can actually see that it is actually redder and fainter systematically because of extinction in that field. So what this means, and what we need to take away from this, is that the tip of the red giant branch is this very simple and straightforward method, but you also still have to worry about extinction if you're not working way out in the halo, like we do in the Carnegie Hubble program. And you have to look for these small scale differences now that we're reaching these precisions. So we use the DEB and the LMC, and we also see consistency with other local group objects, but NGC 4258 is probably gonna tell us more about the ultimate calibration. So our design eliminates a lot of these systematics that I just showed you an example of in 4258, but I'll show you a different example in M101, which is our closest supernova 1A host galaxy. And I was really excited when we started working on M101 because I thought we'd have all these extra fields where we could measure independent tip distances in different fields and start to understand what our field-to-field systematics are. Unfortunately, as was foreshadowed by 4258, these pointings actually still, even though they're far out in the galaxy, still sit in places where we have to worry about extinction. So our measurement out in the halo, which is this green pointing, the A pointing, gets a tip value here, which is shown by this bar. And if we look at these other CMDs, they get systematically fainter and redder as we go into the galaxy. And so that's telling us that even though there might be a lot of halo between us and the disk, because this is a statistical measurement, our triggers and our measurements are going to come off of the dominant population, which is not necessarily those metal poor halo stars that we're looking for. So to control for systematics, we have to go far out into the galaxy. And you can also, it gets even more egregious when you actually plot these pointings on the H1 map from the THINGS project. And you can see just how much gas is actually out there in these outer parts of galaxies. And what this means is more insidious. It's slightly more insidious than just saying, oh, well, couldn't you just measure that extinction and correct it out? And the answer is no, not quite. So this is different luminosity function responses. So where we're looking for that absolute edge for our field, where you can see regardless of how we smooth the data, we actually get a consistent measurement within our statistical uncertainties. This is one of those other fields, and I just picked this one as an example. And this is our measurement here. And you can see that for some smoothings and some ways to measure the tip, you do get something that's very consistent, but that's not a given. And if I didn't know a priori what the distance was from being out in the halo, I wouldn't be able to distinguish this tip from any of these others. And so that's why we have to be very careful with our systematics. So what's left in our systematic error budget? So many of the things, the way we design our study gets rid of a lot of the systematics, but we also have to worry about our technical systematics. And so we do injection tests. We've run multiple different types of pipelines. We look for systematics that happen as a function of signal to noise in the image. And we've also run many, many different types of edge detection to make sure that our results are consistent no matter what the choices are that we make in our analysis. And then when it comes down to it, you can compare objects with both the tip of the red giant branch and Cepheid distances. And so unfortunately, there's only 10 galaxies in common so far, which is not exactly a large statistical sample, but it is encouraging because we do see overall agreement. The weighted mean in this comparison is about 0.06 magnitudes, but the scatter is about 0.17. And so this is a bit of a busy plot because I've actually labeled the galaxies here, but you can see that as we go further away, we do have a few more galaxies scattering pretty far away from that mean, or from 0, 0. And one of them, for instance, is NGC 4038, which is the antennae. So some of this scatter we can explain by understanding that the antennae is just a difficult galaxy to make measurements in, and perhaps by being out in the halo of that galaxy, we're getting a better measurement, maybe not. But some of these others, we just see these differences that it's hard to interpret because it's only 1 or 2 galaxies where you're trying to understand. So our individual distances are quite precise. We actually get similar precisions irregardless of where the galaxy is because we're using a statistical technique. And we're more or less consistent with Cepheids in our distances. So we can talk a little bit about the Hubble flow itself. And the Hubble flow, we actually can use two different data sets in Friedman et al. 2019. We used both the Carnegie Supernova project data set, which had about 99 galaxies. And we also used the SuperCal sample by Dan Skolnick, who will be a panelist later in the week. And the H0, you can see the distributions here. These are the individual measurements from individual supernovae in the two samples. And you get a very consistent results. So there's a difference of about 0.6 in H0 from using these two samples. What does that mean? It's hard to say. They're different samples. But it's also worth pointing out that Burns et al. Used the CSP sample with Cepheids and actually got a higher H0. So what does that potentially mean about our measurements versus the Cepheid measurements? So one way to look at this, and again, we're still in samples of 10, so it's hard to draw firm conclusions. We can take a sigma, but you know, how robustly are we measuring it? But you can compare the actual absolute magnitudes of the supernova that we get by calibrating those local supernova objects with the TRGB, which is this top panel or in red, and with the Cepheids here. So we use the 10 galaxies in common, and you'll see that our calibrations are actually different in the mean by about 0.1 magnitudes. So it's not entirely just the potential extinction or offsets that we have to worry about. Something more fundamental might be happening here, but we have low numbers. So we can also compare directly here between the Cepheids in the lower panel and the supernova for the common system. And again, low numbers. So it's hard to say if we're really getting a different distribution or if we're just not sampling either in this cross-match comparison. It is worth noting that we are getting the approximate dispersion and supernova 1A that you see, say, in the Hubble flow, which is between about 0.1 and 0.15. So seeing anything too concerning there, but our uncertainties in the mean are small and the same, and we are significantly different in this point. So we have multiple Super 1.0 samples that we're using, and those samples are somewhat matched to what you use in the Hubble flow. So the Cepheid, I've only shown you Cepheid comparisons here in trying to evaluate our uncertainties, but the TRGB actually brings galaxies into the calibration sample that will never be calibrated by Cepheids because they don't have Cepheids or they have sufficiently small numbers that you can't actually get, it's not necessarily the best bet to get a distance to that galaxy. So what's interesting about the tip of the red giant branch moving forward is that we will be able to calibrate supernova 1A that occur in low star forming galaxies and lower mass galaxies sometimes, which could be very interesting. Okay, so what's the summary? The Carnegie Chicago Hubble program, we use geometric anchor. The two anchors that we can use right now agree well despite the extinction concerns in the LMC. That is an evolving community discussion. The supernova 1A calibration, our method eliminates systematics, but we still have to be attentive to how we're applying the tip of the red giant branch. Our study was designed to do it in the best way possible, which means that when you're taking measurements from the literature, you have to pay attention to what you're taking and that you've evaluated everything at the same level. And then for our supernova in the Hubble flow, the calibrations are actually distinct between the Cepheids and the tip of the red giant branch. But we're still working in small samples when we're trying to make these comparisons and understand if the difference that we see in the H0 values that we get is telling us something about how we've been measuring them previously. So it's still. So I have just 1 minute, I think. And this week, another hat I wear is the co-chair of the Committee on Inclusion in Sloan. And this is Black and Astro Week. And I would be remiss in my leadership responsibilities if I didn't remind everyone that Astrobites will be doing a series of perspectives from Black astronomers. And it's very important that we read these and that we learn how to use our voices to amplify these individuals. If we can solve a problem like H0 to 2%, I think we can also apply, we can solve the underrepresentation problems where Black astronomers are only about 3% of the annual PhDs. And what I think is really important to understand is that this quote, I like to use quotes in my talk, and I saved my quote for this. Sometimes the greatest way of saying something is to say nothing at all. So not saying anything is actually making a statement. So thank you.
Thank you very much, Rachel. And thanks also for raising that last point. I very much appreciate it. Thank you. So the questions on Slido, the first one is from an anonymous submitter. Why do you think other analysis that calibrate with TRGB from Tully's TRGB pipeline, in brackets IRTF, BTF, and SBF, get higher H0 values than CCHP?
Yeah, that's a really great question. So I think it comes back to what I'm talking about. A lot of the projects, a lot of these calibration projects take the data that's available in the literature. So that's archival data. So the reason I focus so much on looking at these archival fields and how we find these differences, these systematics having to do with extinction, is exactly for that reason. If you take a random pointing out of the HST archive, you're not guaranteed to get a distance at this precision. And you do have to pay attention to those things when you are using these samples together. So reddening is a systematic, not a random. So averaging over many, many galaxies that aren't optimally designed TRGB measurements is not actually going to take care of systematics like extinction.
Thanks. The next question is also by anonymous. Jiang Li 2017 and Reed et al. 2019 got minus 4.01 for the outer field for TRGB. Why do you get minus 4.06 from the same data and distances?
So if you go and look at the Jiang and Li and the Reed et al. So sorry, there's two different papers here. So Jiang et al. Averages the Jiang and Li averages the LMC measurements with the NGC 4258 measurements and get something that's sort of dead in the middle. So their LMC calibration is actually slightly fainter. It's about like minus 3.95. And so minus 4.01 is in the middle. If you read that paper in depth, you'll see that they used this extinction value in the LMC that we're currently arguing over in the literature. And if you use a higher extinction value, you get the LMC measurement that Friedman et al. Published. And so that's the difference there. The Reed et al. Work actually averages the two fields. That number there is an average, I think, is an average of the two fields that I showed you. The one that has actually, it's consistent with about an AI of about 0.15, the inner field and the outer field. And so if you take the average, you get minus 4.01. And I tried to point that out with the M101 data, is that you're not actually just going to get that extinction value. You're not necessarily just going to get the true tip measurement plus the extinction value because it's a statistical method. You're going to get somewhere in between. And that's what I think is happening there. We have a very long, very detailed paper trying to understand this that is close, but wasn't ready for this meeting. So I didn't want to go too far in depth into that.
Great, thanks. So Rob Jaz asking, are the fields for your more distant TRGB SN calibrators more similar to the outer fields in nearby NGC 4258 and M101, or do they have more disk contamination?
Yeah, so those outer in the most distant galaxies do have more disk contamination. So we try to cut out as much of that as possible using both injection tests to look for blending and crowding and the surface brightness. You can actually, and surface brightness maps that come from external data sets to pick regions that we think are safe following the prescriptions and the guidelines of the CCHP program. So we think they're okay, but it would, I would sleep better at night if we had separate pointings. Unfortunately, those are very, very expensive. And it's not necessarily clear that we have the strong evidence to go after those orbits right now.
Great, thanks. And one final question from Marina Raikova. In addition to extinction, there's a question of metallicity effect on the TRGB. How do you correct for that?
Yeah, so thank you for that question. I didn't have time in my narrative. So I've put up a slide right now. This is from my backup material, where I'm actually going to show what they're talking about with metallicity on the tip of the red giant branch. So these are two high, oops, it might be hard to see because I can't show you all my slides. These are two high metallicity galaxies from Zheng and Li 2017, so M81 and M105. And so this is a point diagram and this is a Hess-like diagram, so a density plot. So you can see this is the tip here where these error bars are, and you can see it turned down. So more metal-rich stars, RGB stars, absorb more flux than the optical. And so the metals absorb the flux, and so they are systematically fainter and redder. But this little box here is the color range that we actually use for the TRGB measurements in the Carnegie-Chicago Hubble program. And you probably didn't notice that it was so small because we literally don't have any of these super metal rich stars in the fields that we use. So this is our color box compared to the metallicity comparison. And we actually select this color box based not only on the data that we get from nearby galaxies in their halos where we actually have metallicity estimates, but also from looking at this kind of measurement. And as just a quick, these are the metallicity-based calibrations, and here's that same box from the CCHP calibration plotted here, just to show you, if you're not familiar with some of the other calibrations, we're blue of where we think it's a problem. And our uncertainties also largely encompass some of the variations that are seen in careful measurements, but it's something that we need to keep working on.
Thanks very much. Thanks, Rachel. So next up is Sylvia Galli, who will tell us about Planck and the cosmic microwave background. Sylvia, are you here?
Sure. Hello, everybody. So I'm going to share my screen. I think it's this one, yes. Okay. All right. So hello, everybody. You can hear me well?
Yes.
Fantastic. So hello, everybody. And so let me thank the organizers for reorganizing this entire conference remotely. I think it's fantastic. And I was asked to talk about the measurements from Planck and the cosmic microwave background, and a lot of the material of this talk is taken from the cosmological parameters paper that we published a couple of years ago from Planck, and the likelihood paper that we published last year. As many of you know, Planck is a satellite that observed the cosmic microwave background for between 2009 and 2013. It observed the sky with nine different frequency bands between 30 and 857 gigahertz. And all of these frequencies allowed us to disentangle the CMB emission from astrophysical foregrounds. And 7 of these channels were actually sensitive to polarization. And this is really great because all of this information has been incredibly helpful in constraining cosmology, as I will show you in a moment. From the satellite, we had, from this data, we had 3 data releases. The first one was in 2013, based on what we call nominal mission, was about 1 year of data. And our results were based only on temperature, temperature and isotropies. In 2015, we more than doubled the data that we used for the release. And for the first time, we showed the power of polarization to constrain cosmology. Constraints on cosmological parameters decreased by 30 to 50% just by adding polarization. However, at the time, we already knew that there were small remaining systematics in polarization, and we really spent a lot of time, 3 years, working on essentially the same data as 2015 in order to better understand these systematics and clean the data to have the best possible legacy release. And this work has been incredibly successful, and we were able actually to clean the data from such effects. So across all of these releases, what's interesting is that the Planck value for H0 didn't really change across the years. So what I'm showing you here is a bit the timeline of how the tension grew from the first release in 2013, where we had a measurement of H0 of 67.3 plus minus 1.2. The error bar was double or a little bit more than double with respect of today, essentially because this was based only on temperature data and just nominal emission. And at the time, this difference could still be accounted maybe as a statistical fluctuation when compared to the SHOES program measurement, or even with from the measurements of Wendy Friedman and collaborators. And then across the different releases, you can see that the mean value from Planck didn't really change. It remained stable around 67, with the error bar, as I said, that decreased by more than a factor of 2. But what really increased the tension with direct measurement, I would say, is the fact that the measurements from the SHOES program decreased from 2.4 in 2013 to 1.5 kilometers per second per megaparsec today, and which led us to this 4 sigma, and again also very stable results. And then if you want 5 or 6 sigma or even more, then you need to combine the SHOES measurements with some other measurements of H0, either the time delays or the masers. And it's, I just wrote it here. It's good to keep in mind. And as we already heard from Rachel, and I'm sure that there will be a lot of discussion about this, this is challenged in a way by the measurements from the tip of the red giants. But so these different measurements from Planck, very stable across the releases, and assumed clearly the lambda CDM model, which is a very good model to describe our data that I show you here. As you know, the CMB is distributed as a Gaussian random field. And so all the cosmological information we are interested in is contained in the 2-point power spectra. And here I show the temperature power spectrum, the cross correlation between temperature and polarization, and then the EE power spectrum in the bottom. And also in our baseline, we use the small non-Gaussian signal left by gravitational lensing to reconstruct the lensing potential. And the blue line is a fit to the data, assuming the lambda CDM. And from qualitatively, you can see from these plots already that it's a very good match to this data. And so since the model is good, we can measure the 6 lambda CDM parameters that are a couple of them to measure the shape of the primordial power spectrum, the angular scale of the sound horizon, which is very important for the H0 measurements, which basically regulates the position of the peaks in the spectra, the optical depth to ionization, and then we have 2 parameters that govern the density, the physical density of baryons and dark matter. And each of them have peculiar impacts on the power spectra. Here I show only temperature. But these effects are highly correlated between each other, and I will show you in a second an example of this. So through these effects, we could estimate cosmological parameters, which I show you here. These are the first 6 are the lambda CDM parameters that we measure at the sub% level. In some cases, in particular, the acoustic scale of sound horizon, we measure this at the 0.03% level. And the reason for this is that we really observe extremely well a lot of the CMB peaks. We observe 7 of them in temperature, 6 of them in the cross correlation with polarization, and then 5 in polarization itself. And you can also see that the uncertainty on the Hubble constant effectively is a 0.8% relative uncertainty. This is the best indirect detection or indirect determination of the Hubble constant, but as I will tell you in a second, it's not a direct measurement. So as I said, these results have been extremely stable, and this is quite striking because from a data release to the other, we changed a lot of different things. So the most trivial ones are just that we doubled the data, we added polarization, we changed particle parameters, and many others. And no one of these changes really changed our main scientific conclusions. It essentially changed error bars, and the changes between the different releases are extremely well understood. The lambda CDM model is a good model to defeat. However, we do have some 2 to 3 sigma curious outliers, if you want, in some extensions of the lambda CDM model. However, the reason why we don't claim for evidence for new physics is that whenever we then combine with other data sets such as BAO, or even when we add the CMB lensing measurements to the CMB anisotropy ones, most of these deviations go away. So whether these are statistical fluctuations or something interesting that is going on, either it be new physics or a small level of systematics, is still unclear. But we, for what we could say is that these deviations we see today. As I said, this measurement from Planck relies on a model. And the reason for this is the one that is shown here, and I'm sure that Lloyd and other people will discuss this further during this conference. But essentially, the point is that the CMB is not directly sensitive to what happens today. So essentially, the expansion rate of the universe today. But what it measures is this angular scale of the sound horizon that I just showed you. We measure extremely well at the 0.3% level. So this is essentially an angle, and we are interested in inferring from this angle the angular scale, the angular distance to the last scattering surface. And in order to do that, we need to have the physical length of this angle, which is the sound horizon. And the sound horizon can be calculated just as the integral of the sound speed and the over the expansion surface, and this is important. And these quantities only depend on the baryon density, the dark matter density, and the radiation density that we infer from, for example, COBE. So if we have a model, we can calculate this quantity. We have theta s, and so we can infer the distance, and then we can link then the distance to H0 through a model again, because this is just the integral of the expansion rate or the inverse of the expansion rate now from the last scattering surface until now. And you can see clearly that H0 appears in this relation together with other cosmological parameters such as omega m. But so one point that I want to make is that not even thinking about extensions of lambda CDM, but already within lambda CDM, the different parameters are extremely correlated. So what I'm showing you here is the correlation matrix of the cosmological parameters. Here are, again, the 6 lambda CDM parameters, and here are derived ones such as H0 and omega m. And you can see that H0 is correlated with, for example, the dark matter density, the physical dark matter density, and the anti-correlated by 96%. And it's correlated at 98% with the big omega m. And this is just to underline the point that the CMB measures a combination of these parameters that gives you the power spectrum that then you compare to the data, and not each of these parameters individually. And I just underline this because recently there have been a few papers basically taking omega m from Planck and then varying without, changing omega m, varying H0, and see whether their high redshift objects were sensitive to the value of H0. And this is wrong in a way, because Planck doesn't give you a measurement of H0, which is independent of these other measurements, in particular H0. The second point I want to make about degeneracies is that you can play the degeneracy game in order to try to alleviate the Hubble constant tension, in the sense that you can extend the lambda CDM model and hopefully find a set of parameters that are degenerate enough with H0 to increase the error bars and try to alleviate in this way, to lift the tension that we see in the lambda CDM case. Now, we try to play this game, and clearly, hopefully, even better if in an extended model, also your mean value changes to 74 or close to that. However, in the classical extensions that were tried in the parameters papers from Planck, no one of the extensions of lambda CDM, such as the number of relativistic species, the playing with the shape of the primordial power spectrum, or curvature, or other extensions, really neither shifted H0 to high values or higher than 68, or increase the error bars enough to accommodate this difference. So in some way, more sophisticated extensions are needed, and the main reason is that we have so much data in Planck, in the CMB, and more generally in cosmology today, that it is very hard to find a model that actually can do this. But so I will not go into all of the tests that we've done to prove the robustness of the data. As I said, we spent an enormous amount of time to show that, anything we could think of, any kind of possible systematics for current cleaning and so on and so forth, could actually account for this difference, and we didn't find any good candidate for this. However, one might wonder how much consistency there is between different CMB experiments. And that's what I'm showing you here. Clearly, we had already the WMAP measurements that at the time gave an H0, which was 70 plus minus 2.2. The ground-based experiments, such as SPT and SPT poll, and then also the results from ACT, in particular ACT poll. And as you can see, ACT poll gave a value of H0 which is centered on the Planck value, although with a much larger error bar, almost 6 times larger. But WMAP and SPT are more around values that are around 70 or even higher. So first of all, one can say, all right, but these are measurements that have quite large error bars. And so what happens if we add BAOs in order to decrease these uncertainties and have a better comparison? And if you do so, in most of the cases, H0 again comes down quite low. And the second thing that you can do is to say, okay, but I would like to directly compare these different CMB measurements and try to see whether they are consistent. And the difficulty in doing this is that clearly these are experiments that observe different ranges of multiples and different fractions of the sky. In particular, both WMAP and Planck were full sky experiments, but Planck, basically the signal to noise of WMAP is going rapidly to zero, say after multiples of 800. So you can compare well WMAP and Planck, but at low and intermediate multiples. And on the other hand, for example, SPT observed only 6% of the sky. So what you can do is to measure power spectra for Planck on the SPT patch, eliminating this way in the difference between the two, the cosmic variance, and directly see whether the measurements are consistent. And also, while SPT is a much more higher resolution experiment than Planck, you also need to limit yourself in multiple range in order to directly be able to compare these two. And in both these cases, these were shown to be consistent with Planck. So if you compare Planck and WMAP on the same multiple ranges, you get the same values of H0. And this was also beautifully showed in this paper in 2018. At the power spectrum level, Planck and WMAP agree extremely well. And on the other hand, on the same patch of the sky, as observed by SPT, and on the same multiple range as observed by the two experiments, Planck and SPT-SZ agree extremely well in temperature. In polarization, the comparison between Planck and SPT pole is less clear. There are differences at the level of a little bit more than 2 sigma. So whether these are consistent or just a statistical fluctuation, this is still something that needs to be confirmed. In this 30 seconds remaining, I just want to mention that, this CMB doesn't only mean CMB anisotropies or primary CMB anisotropies, it means also CMB lensing. And you can actually combine the CMB lensing reconstruction measurements, for example, from Planck with BAO and measurements of essentially the baryon density from deuterium abundances and BBN calculations to infer H0. And also in this case, you get values of H0 which are low, centered on the Planck baseline. And again, this is very curious. The SPT pole CMB lensing, on the other hand, gives somewhat higher values. And there is this recent paper claiming that this is essentially driven by a possible 2 sigma difference between Planck lensing and the BAO. But essentially, the problem of all of these small differences is that they are small at the 2 sigma level, and overall, these experiments give a pretty consistent picture in the CMB field. And just to conclude, the future is super bright for CMB. There are ground-based experiments observing from the ground small-scale polarization, and they have the potential to measure H0 with the same accuracy as Planck, or even better in combination with it. Thank you very much.
Thanks, Sylvia. So jumping right into the questions, the first is, what is your take on the difference in H0 between low L and high L measurements from Planck? I guess you already started to speak about that.
Yes. We worked really a lot on that issue, and that issue is related also to the fact that when we fit the full spectrum with the extensions of the lambda CDM, such as with the A lens, so in excess of lensing, or anything that can mimic a smoothing of the small scales in the CMB anisotropies, we have deviations from lambda CDM at the 2 to the 3 sigma level. And the problem is that we've done the work of asking ourselves whether the two data sets are in agreement. Essentially, if you take, what happens below L of 800 with together with what happens at L of larger than 800 in the power spectrum, and you measure cosmological parameters from the two ranges, you can ask yourself whether the parameters that you get are consistent, and they are consistent at the level of 2 sigma. So what do you do with 2 sigmas here and there? We just need more data to understand whether these are, there is really something there, or these are just statistical fluctuations.
A question by Anonymous. What's your take on the fact that SPT pol is mildly discrepant with Planck? To phrase it otherwise, LCDM and Planck is not a very good fit to SPT pol data.
Yeah, so I think that measurement is a really nice measurement. I think it's not completely understood whether SPT pol is consistent, for example, with the SPT pol with the other measurements in the same patch of the sky. The chi-square of the SPT pol data with respect to lambda CDM, when you fit those data alone without even Planck, are not, the lambda CDM is not a completely good fit to those data at the level of a couple of sigma. So once again, whether there are small residual systematic lurking or these are statistical fluctuations, again, it's hard to say.
Thanks very much again, Sylvia. So we have to move on to the next talk. Lloyd Knox will now be telling us about the theoretical picture behind the Hubble problem. Lloyd, are you there?
Yes, hi. Let's see, let me share my
While you're
screen.
setting up, I would like to remind people you can still submit questions to the previous talks and upvote the questions so that they can be discussed during the discussion panel.
All right, thank you very much to the organizers for persisting in the face of these difficulties. I'm anyway delighted to be virtually here and getting these updates on this really interesting problem. So most of what I'll be presenting here, to the extent it's my own work, it's work I've done in collaboration with these people I show here. And I'm talking about 2 papers in particular. This sounds discordant paper with all these people here, and then more recently what we called the Hubble Hunters Guide. And this audience may not know this is an allusion to a particle physics book, the Higgs Hunters Guide, first authored by my colleague here at UC Davis. And unfortunately, our title hasn't survived the physical review D review process, and now it's lost all poetry, in my view, becoming Hubble Constant Hunter's Guide instead. But I still think of it as the Hubble Hunter's Guide, or in my really, I think it would be more appropriate to call it a Hubble Hunter's Guide. So I've been asked to give the theoretical picture. So let me jump right into that. So I think that it's really helpful, at least from the perspective of thinking about what are our possible ways out of this in terms of a change to the cosmological model. I find it very helpful to think about not only the Hubble constant being off, but also the sound horizon. So here in this plot, we have the Hubble constant on the y-axis and this sound horizon on the x-axis. So how far a sound wave will propagate in the primordial plasma from the beginning until the plasma disappears. And here's the constraint from Cepheids plus supernovae. And then if we, you know, and there's no assumption of lambda CDM here in this constraint. And if we can take the combination of baryon acoustic oscillation measurements and Pantheon measurements and do a fairly cosmological model independent constraint, and this boils down to giving a pretty tight constraint on the product of the sound horizon times the Hubble constant, and that's this green band here. And then if you assume this lambda CDM model that Sylvia has nicely introduced, and use the Planck data, then we get these. Here's the predictions for the Hubble constant and the sound horizon, the constraints on these parameters that then arise with that conditioning on Planck data. So we're off not only in the Hubble constant, but also in the sound horizon to some degree. I mean, we would like to be here, and this is where, you know, these data, which, you know, don't rely on lambda CDM, should say we should be in terms of the Hubble constant and the sound horizon. And this is right. This is an interesting opportunity for theorists. Our goal is to find model X, which, you know, brings us over here. So restores concordance, not only in this plane, but other also with other data sets, is compelling and beautiful, makes predictions that are subsequently confirmed. And actually, one of the things that makes this an interesting problem to pursue as a theorist is that I think it's inevitable that that new theories, any new theories that solve this problem, will make predictions that are testable by CMB observations in the near future. And also that there's progress happening on the distance ladder side as well. So we have not yet found a model X, I'd say. There's been a lot of effort. So here's some papers on theoretical solutions that have been published in the past 9 months. Here's some more. So there's a lot of activity, and you might ask, why don't we have a model X yet? And I have a picture of a straitjacket here because of thinking about something Richard Feynman once said about creativity in theoretical physics. It's creativity in a straitjacket. And we have, as Sylvia has shown, lots of things confining us. Just these, you know, really precise measurements of statistical properties of our universe with a lot of richness to them. And lambda CDM has done an extraordinarily good job. So here's the temperature power spectrum with residuals. I'll just go through the CMB stuff. I'll actually just go through all of this quickly. You've seen this from Sylvia. These are fits to lambda CDM. Here's the with polarization data from Planck, ACPOL, and SPT pol. I agree with Sylvia's assessment. We have problems with lambda CDM with just the SPT pol data alone, but these are at the couple sigma level. And then also we have the inferences of CMB lensing. So this is a deflection angle power spectrum with measurements from Planck and SPT. All of these are present a good deal of consistency with lambda CDM. So we have these data sets, but we have many more that bear on the problem. Here's a compilation of BAO measurements over this range of redshifts here. We have the uncalibrated supernovae from, for example, the Pantheon collection, giving us constraints on luminosity distances across, out to z of about 1. These Adam referred to these as guardrails. The combination of these supernovae and BAO really help to cement the H0 predictions from really narrow, us into particular values of H0 from a variety of different data sets. This, at least in the Lambda CDM model, we have redshift space distortions constraining the growth rate of structure. These present constraints on departures from Lambda CDM. These are, these curves here are Lambda CDM fits to Planck data. There's measures of, other measures of inhomogeneities in the more recent universe. Here's cosmic shear data from DES. And then there's also light element abundances, which are constrained, for example, from quasar absorption line systems shown here. So there is a lot of data to contend with, and we're finding these data to be highly constraining. So we do have a model, though, that's doing a pretty amazingly good job at agreeing with all these data, with only 6 adjustable parameters, as Sylvia had mentioned, and that's Lambda CDM. There are some issues. Those came up in Sylvia's talk, and also the sigma 8 tension, as far as agreement with all these data sets that I just very quickly went through. But all in all, the agreement is really remarkable. But somebody needs to mute their microphone. Of course, there is this 4.4 sigma discrepancy with H0 from Cepheids plus supernovae, or 4.2 sigma, and there's a greater than 3 sigma discrepancy with strong lensing time delays, and that's why we're here, and this is why we are searching for model X. But it's worth considering some of the things that Lambda CDM gets right and how impressive they are. So one of the huge effects that imprints a large difference in CMB maps is photon diffusion or silk damping. And if there were no photon diffusion, then in the Lambda CDM model, the power spectrum would look like this. But there is photon diffusion. It's the reason why the spectrum instead looks like this down here. This is a huge L-dependent effect. It's in order to get it right, there's complicated atomic physics calculations that have to be done. This is an out of equilibrium process. Saha equation is a horrible approximation to this, and Lambda CDM gets it right. There's a whole bunch of other effects that go into getting Lambda CDM right that I could go through, except we don't have time. All of these effects listed here are significant. Any contending model has to get them right. I think that we could do more to demonstrate this explicitly, and it would be helpful for exploring extensions of Lambda CDM, for coming up with extensions of Lambda CDM and thinking through more quickly whether they're going to work or not. I think we can do more to kind of deconstruct our modeling of the CMB and the influence of all these effects. And an exercise of the type I'm imagining was conducted recently by Pavel Motlach, so I just want to highlight that here. He was looking in particular in this paper about testing the consistency of the baryon density as inferred from the Planck data, and he identified 8 different physical effects by which the baryon density makes its impact on the CMB power spectrum. And he split the baryon density parameter into 8 different parameters, with this unphysical model in which these 8 different, these were 8 distinct parameters. So you could vary them independently, and you can look for their influence on the power spectrum, and you can constrain them independently. So here's the 2 most important. So that impact on diffusion damping, and also the baryon reduction of the plasma pressure. And you can see the constraints from both of these, and they're consistent. And these are from entirely different physical effects. And it helps to highlight, I think, the non-trivial success of lambda CDM. So how do we get the Hubble constant from the CMB data? I think that's helpful to see in the context of lambda CDM. It's very similar with any other model. So let's go through this. Sylvia spoke to this to some degree. So the sound horizon plays a really important role in this. That's our standard ruler, and we need to calibrate it. And so we calibrate it, using this model. So in time dt, right, the sound wave travels a physical distance cs dt, or scale factor times this change in the co-moving distance, and we can then integrate that up and to get the sound horizon. So if we know this, when the plasma disappears, and if we know h of a and we know the sound speed, then we can calculate the sound horizon. These depend on the sound speed and the expansion rate depend on these parameters of the model. The sound speed just depends on how the pressure changes, the density changes, which depends on the baryon to photon ratio. And the expansion rate, at least in this epoch of interest here, where we have no cosmological constant, at least in lambda CDM, then we have, here are three contributors to the total density. And these are, rho gamma is not a parameter of the model. This is basically pinned down by phi-res observations, and then that and model assumptions give us the density in neutrinos. And so the only thing left to adjust is rho matter. How do we determine these things? Well, for the baryon density and the sound speed, you can see Pavel Motlach's paper, for example. But this is actually fairly direct. We have fairly direct constraint on this parameter that we need, because this is telling us the pressure of the plasma. It impeaks the 0 point of these oscillations, and therefore the peak morphology. And then the matter density we infer from this radiation driving effect that I don't have time to go into, but is basically due to how gravitational potentials decay as the oscillations get underway, and the amount of resonant driving that occurs because of that potential decay is sensitive to how deep in the radiation dominated era these oscillations start happening, and that gives us our sensitivity to the matter density. So Sylvia showed this triangle, right? I just went through how we calculate this. Then we measure this angular size of the sound horizon, which right can pretty directly be read off of the spacing between the peaks. That this spacing is related to pi over theta s roughly. And so we have this distance then inferred to a single redshift, and we can then go on to step 3, which is to get the right angular diameter distance. We only have one thing left in the model to adjust, right? We've pinned down the baryon density. We know what the matter density is. We know the radiation density. The only thing to pin down is the cosmological constant. So we have a distance measured to 1 redshift. We are way out of the low Z region where Hubble's law applies, but we do only have just one free parameter left to adjust. That's the cosmological constant. With that done, we know the model predicts H at all redshifts, and certainly at Z equals 0. So let me say something about the search for model X. So again, right, this is here's our goal, what we're looking for in Model X, and in our Hubble Hunter's Guide, you know, in a nutshell, the statement there is, yeah, Model X probably includes a lowering of the sound horizon, right? So we got to get from here over to here, and if you're going to do that, that means additional components must be important in this interval in redshift. So let me explain this figure. This is, sorry, this is a bit complicated here. All we're looking at here is, at a given redshift, how sensitive is the sound horizon to variation of the Hubble parameter? And we see that that if you're going to influence the value of the sound horizon by changing the Hubble parameter, you've got to do it in this region. This is where the sensitivity is. So a lot of the efforts are at a lot of the efforts at Model X are adding additional contributors to the energy density and therefore the expansion rate in this redshift range. So what's the state of the art? So one way of increasing the energy density there is by adding light relics. But as Sylvia said, as Sylvia showed, just the vanilla light relics doesn't work. So there needs to be extra ingredients added. Here's a couple of uses of light relics with extra ingredients. Another way is by just adding in some scalar field with some effective potential, and these go under the name early dark energy. And here's some of the investigations here. And then there's a variety of other things to do. So here's a recent example of taking warm decaying dark matter. So this behaves like radiation early on, and then starts to behave like matter as we approach matter radiation equality, and then decays and becomes like radiation again. So you do get this extra contribution to the energy density around matter radiation equality, exactly where you need to do this to lower the sound horizon. And this is kind of typical of these models, though, where so here's adding in more of this stuff, more of this warm decaying dark matter for different particle masses, and you see that you can get the Hubble constant to go up, but it's hard to get it to go. It doesn't really go up. That doesn't really like to go up much beyond 70. Never mind getting up to more like 74. These are the Rees et al. 1 and 2 sigma confidence regions.
Lloyd, sorry, you're eating into your Q&A time now.
Oh, no. Okay. So let me then, I think Evan will speak to these remarks. So let me just skip over this, except to say that these other data sets become important too, and if you're searching for a complete concordance, and move on to my conclusions. And let me not go read through my conclusions, but I did want to add just a couple comments on racial justice, and that is that I think it's really important that it's been very impactful for me to discover my own biases, and I really encourage people to do that. I think it's a really important step towards then being responsible for them, and I've known about them theoretically, but to actually do one of these tests, which you can find from this link here, really gave me a felt experience of my own racism, and I think it's a powerful thing for people to do. And I just wanted to echo what Rachel Beaton brought up. So I better end there. Thank you.
Thanks very much. So a question from Fred Coban. Similar question to the previous talk. To change RS, you can also change CS. Are the current assumptions on plasma physics good enough to infer the sound horizon?
Okay, so yes, that's absolutely right. To change RS, you could also change the sound speed. And maybe there's a way to make that work, but we're actually, you know, the spectra are actually fairly sensitive to what the sound speed is. So changing the sound speed is, you know, changing the pressure density relationship in the plasma. And, you know, you can forget models of the plasma for the moment and just look at, well, what are we inferring empirically about that pressure density relationship? And it's exactly, you know, that pressure density relationship that is giving us the offset to the 0 point of the oscillation that leads to the odd even peak height modulation that is the dominant source of our information about the baryon density. And so it's, you know, we're kind of somewhat directly probing that sound speed with these measurements of the power spectrum, and then we can go look to well, is that consistent with other inferences of the baryon density? And you know, it appears to be consistent with observations of light element abundances.
Thanks. And then a last question before we go on to the discussion panel. What's your take on the assumed perfect flatness of the universe?
That's a great question. I mean, I guess one thing, right, so that first, I guess one pedantic thing is that, you know, to me, lambda CDM, you know, and Sylvia listed the 6 parameters, lambda CDM includes this assumption of 0 mean curvature. So I'm always a little confused to see people say flat lambda CDM. Anyway, that is, when people talk about lambda CDM, usually they mean, you know, exactly this assumption that there is 0 mean spatial curvature. I think looking for evidence for non-zero spatial curvature is, you know, incredibly interesting. It would be really fantastic to have a you know, manage to convince ourselves that we discovered non-zero mean curvature for its implications for early universe physics and inflation. There are, you know, there's this curiosity that if you just use the Planck, TT, TE, EE, you know, those power spectra, you find that there is, you know, around 3 sigma evidence for the curvature to be non-zero. And but so I think that's a, you know, an interesting fact. But then if you take that seriously, you kind of have to just ignore, you know, like everything else we know that bears on the question of curvature, in particular the baryon acoustic oscillations or CMB lensing. And so I don't think there's a significant case now that we've seen a departure from 0 mean curvature.
Great, thanks very much. So now we're up for the first discussion panel of the conference, and I would like for all the panel members to please turn on their videos. So that would be Adam Rees, Rachel Beaton, Sylvia Galli, Lloyd Knox, Behnam Javan Mardi, Evan McDonough, Dragan Hutter, Jeremy Mould, and Wendy Friedman. Hi, everyone, and I will leave the floor to you.
Good morning, everyone. let's see, I'm Dragan Hutter. I volunteer to collect slides and maybe guide the discussion of the panel. So with that, let me maybe start off. First of all, thank you everyone, thank you organizers. For those of you who are wondering if Twitter is good for anything, like I do sometimes, I learned about this conference from Daniel Skolnick's Twitter feed by randomly checking it out one day. So yes, Twitter is good for something. It's good for learning about this conference. But we have a nice panel now. We have Benham Javanmardi, Evan McDonough, Jeremy Mould, Wendy Freeman, and I. And also we have speakers earlier in the day. I think we agreed to go through some slides, which I've posted in the chat, so you can all check them out. I think I will also share my screen. I think that makes sense, unless if I hear otherwise.
Yes, please do.
Yes, okay, thank you. I will go through a slide or two for everybody. Let's see, let's maybe all agree to take no more than maybe a couple of minutes per person, just in order to finish and to hopefully have some time for questions. So a couple of minutes, whether you have a slide or two slides, and some people didn't post, maybe they want to say something. So with that, I propose we start with slides. So let me share screen. And like I said, the link is in the chat. So can somebody give me verbal confirmation that you can see the slides?
Yeah, got it.
Yes.
Yep.
Okay, great, thank you. So let me start off. I'll start off with slide 2, with my slide, and then we'll go to other people. Now, I think, let's see, there are lots of models out there. So I'm gonna take a little bit of a high view of the situation. There's lots of models out there, theoretical models, to explain the Hubble tension. Lloyd has at least one. Many of you have one, I have one. But in all honesty, there's only one simple model, one really simple model, one preferred model to explain it, which is simply cosmic variance. We happen to live in an understanding region. Things happen. Yeah, we know it's unlikely, but it can happen. So lots of people have gone back and forth on this, and some theoretical papers were written. And I was really, what changed my thinking about the situation is to learn how strong the result against this is. So Heidi Wu and I decided to check this explicitly a few years ago. We took a very large n-body simulation called Dark Sky. We subdivided many subvolumes, put observer in each subvolume, lay out supernova on the sky, find closest matching halos. You measure H0. In fact, you don't even, you go directly to delta H0 because it's co-moving coordinates. It gives you directly the fluctuation away from the presumably CMB mean. And you repeat that many times for subvolumes and also for relative rotations between the subvolume and the supernova coordinate frame. And when you do that, you find that there's a very, very small cosmic variance in a lambda CDM universe, 0.3 kilometers per second per megaparsec ballpark. That's 1/20th of the value you need to explain the Hubble tension. The reason for that small number is basically the supernovae go out pretty high to 0.15, Z max of 0.15, and that really drives that number down. So it's not just unlikely that cosmic variance, it's completely impossible that cosmic variance explains or even alleviates this in a lambda CDM universe. The only assumptions in this were lambda CDM and that velocity bias is close to 1. That is to say that halos velocities match that of galaxies, which has been checked out independently very well. So that to me makes this really interesting in that the only proposals left are those that modify lambda CDM, the kind of quote unquote crazy models, right? And so that really changed my thinking in this regard. Challenge for theorists, I'm gonna echo some of what Lloyd said, almost word for word. Can you find a compelling model? Aesthetics should matter still, after all, I think. That is favored by the data, that's absolute number 1. If you add 2 parameters, your chi-squared has to be better by whatever number. And that nearly fully resolved H0 tension, that's very interesting. Lloyd also mentioned this. Most of these, all of them that I'm aware of, proposals, they are favored by the data, but they raise global H0 to something like 70, not 73 or 74. They have a surprisingly hard time on H0 itself, even if they are favored by data. And can these models also help resolve some other tension in cosmology? That would be really nice. So this echoes some of what Lloyd said. Question for theorists. And with that, I think let's move on to the next panelist, who is, let's see, Benham has a couple of slides. Benham, you wanna go ahead?
Hello, everyone. Thank you, Dragan. Also, thanks to the organizers for organizing this nice conference. The questions here that I have basically for the shoes team are about the uncertainties of analyzing photometric analysis of cepheids. I've tried to read the shoes papers in details, and the more I read, the more I understand what a great work shoes has done, and I keep learning. These questions are also in line with that. I would like to learn some details of this interesting tension. So here I'm showing you, maybe I can, yes, show my cursor here. The Wesenheit magnitude is here that I'm showing you. This is what is being used by Shoes project to obtain the PL relation, the period luminosity relation between the cepheids, for the cepheids in supernova host galaxies. And the total, and these V, I, and H are the HST bands I'm showing you here. And the Wesenheit magnitude is the reddening corrected. So the total uncertainty.
Are you? I don't see any movement of a cursor.
Oh, you don't? Sorry.
Oh, well, yes, I do, but I don't see any measurements if you were presenting measurements just now.
I don't see it either. So maybe, Behnam, you can just say in words which term you're talking about. And
okay, but yeah, okay. The blue formula Wesenheit magnitude, and so the total uncertainty of this magnitude is written here. This is a screenshot from Rees 2016 paper. The sky contribution is from the crowding bias, which was discussed in Adam's talk. There's intrinsic dispersion. There's also a correction or an uncertainty for having a few number of points for from the different phases of the Cepheid pulsation for estimating the mean magnitudes. But my concern was about this term, CT term, which I found from table 2 of Rees 2016, Rees et al. 2016, and the companion paper Hoffman et al. 2016, that is just the uncertainty from the for the crowding bias estimation. So I was thinking that, is it wrong to expect to see another contribution to this term from the uncertainty of the V band mean magnitude and the I band mean magnitude, and also the R band, the R value, which is the ratio of amplitudes. And if Dragan goes to the next slide, I will ask my second question, and then I will stop. And that is that I couldn't find the uncertainty of periods in the papers of Shoes team. And I know that the contribution is very, very small, but I was wondering that because the period alongside the mean magnitudes and amplitudes are obtained from fitting templates to the Cepheid light curves. How much is the contribution of the period uncertainties? And it would also be nice to have them for further analysis. I stop.
thank you, Behnam. Thank you. Next up, Evan.
Okay, well, let me first try to answer Behnam's question just verbally. So the uncertainty in the Cepheid, you could probably go down to slide 7. The uncertainty in the Cepheid periods are typically 1 or 2 days. So in log period, they're typically about 0.01, and multiplied by the slope of the PL, which is usually around 3 magnitudes, it contributes about 0.03 magnitudes in the scatter of the PL. Now that's 10 times smaller than the scatter of the PL, so it's a very subdominant term. But in terms of systematics, I presented some results that if you do a very large selection, either manually or with a pipeline or with 3 different observers, then those variations in period average out so that the net effect is very small. That CT term, I think, was a color term. Their part of the point is that the R in front of it for the infrared is a very small number, like 0.3.
Right.
And so this generally has a small effect, not to mention that the crowding in VNI is also substantially less and largely cancels in the difference, V minus I.
Mm-hmm.
So I think those are your answers. If I could go back to slide 7 for a minute, Dragan. I wanted to make the point, or this question really, about different ways of calibrating and how we see somewhat different results. So there are a few more recent surveys using tip of the red giant branch for calibration, coming from Tully's catalog for the infrared Tully Fisher, the baryonic Tully Fisher, or surface brightness fluctuations, which are tending to give something more like 75 or 76. So trying to understand the difference between that and the CHP version, which tends to give closer to 69.8, it's not clear or not whether it's a calibration. So if I go to the next slide, this is my attempt to put together sort of some attempt to understand this. So as I said, there has been a host of papers that have been studying the LMC reddening, and that's, I think, because it's a hard problem. So I'm not saying it's an easy problem, but you can track the different estimates of LMC extinction as they propagate to different estimates of the luminosity of TRGB, which for the same or even different supernova samples track to these different values. And I identify the different groups here. So, depending on what that LMC reddening is, it's realistic to get a Hubble constant of sort of 73 to 69.6. Now, I had thought NGC 4258 would be the kind of solution here because there is no reddening to worry about. And I had taken results from recent papers, Zhang and Li, and Reed, Pesce, and Reese, and they got a somewhat less luminous TRGB that would argue for something that is quite consistent with the Cepheids when you use 4258. If you use the Pantheon sample, you get 71.9. With Cepheids, you get 72.0. And I clip out there the Zhang and Li minus 4.02. So I was surprised in Rachel's talk, she mentions that the CCHP is now getting minus 4.06. Which would bring it back to the LMC calibration. And since that one is pretty straightforward, it's just a measurement of the peak and the distance. Maybe when Wendy gets to her a few minutes, you could say something about why those are different than the literature values.
Thank you, Adam. Thank you. Well, let's see. I propose we go back to Evan and then Wendy. Let's do that.
Hi there. Hi, I'd like to first thank the organizers for giving me the opportunity to be on this panel, and I'll try to be brief because I guess we don't have a ton of time. And I'd like to connect with Lloyd's talk and present a couple of new results regarding one of the most well-studied resolutions, and in particular in this class of models that decreases the sound horizon, RS. And it goes by the name early dark energy. And the punchline here is that the premise of the early dark energy model is to introduce a new parameter, degeneracy, in the fit to the CMB. And you can see that in the top left. It's a degeneracy between H0 and the amount of this early dark energy. Now, this brings with it new correlations that you can really understand from very simple physics. And we talk about that in the papers. And as a result of these additional correlations, for example, with the physical dark matter density, the degeneracy is broken by large-scale structure data. And ultimately, this leaves no room for resolving or really even addressing the Hubble tension. So we've seen this in two papers. The first here from March, and the second that appeared last night, so hot off the presses. The second one here is utilizing the effective field theory of large-scale structure. And in both cases, we find H0 values in significant tension with shoes. So I'd love to go into details about what exactly was done in these papers and the physics behind it. But the take home here is that the large-scale structure data breaks the degeneracy of the model extension. And I guess the question I would put forward is, given this situation where we have such precise data from large-scale structure and from the CMB, given that we are trying to do creativity in a straitjacket, do we have a do no harm requirement for a successful resolution? Or is it really the case that, as Adam said, the ultimate, the CMB versus shoes is the ultimate end-to-end test, and that's our goal here? Or do we have to consider the global picture? And I guess depending on your answer to that question, I would pose a follow-up. So do we have an early universe resolution to the Hubble tension?
Thank you, Evan. Just one quick follow-up here to understand. Why is your smiley face getting unhappier as you go to the right in these slides? What thing is going on?
So the top left, you're happy because you have a degeneracy between H0 and the fraction of the energy density of the universe inside this new component. But then you realize that moving along this direction is also moving along increasing the visible dark matter density. And then this also gets encoded in the S8 parameter. And so these two new correlations is sort of confusing. I'm not sure how I feel about this. CMB can accommodate it, but so maybe we're okay with this. But then you look at electrical structure data and you become sad because in particular, this S8 correlation is ruled out pretty strongly by, for example, the DES set of 3 two-point correlation functions from shear and galaxy clustering.
It just rules out that value of S8. Okay,
yeah.
Right.
So you go from happy to unsure how you feel to sad.
Good, good.
Very
okay.
emotional.
On that downward spiral, let's go on to, thank you, Evan. Wendy, I'm on to slide 6. And Wendy, either you're not there or you're muted.
She's muted.
Sorry, yes, I'm muted. So I thought maybe I should first just answer Adam's direct question about calibration of the TRGB. And I think, so our differences come, as he noted, in the value of the extinction to the LMC TRGB stars for the LMC. But as Rachel was presenting in her talk, we now have analyzed a large data set in NGC 4258. And unlike the Reed et al. Calibration of the tip of the red giant branch, the 2019 paper by Reed et al. And Reese and collaborators, where they did their TRGB measurement was in the disk of NGC 4258. And as Rachel showed in her talk, that's a field that is in a region of star formation. You can see the blue stars. The HM map shows there's lots of gas, there's dust in that field. The Cepheid measurements, the parent distance modulus for V and I indicate that there is reddening in that field, and yet they don't make a correction for reddening. So our difference, when we get a calibration of minus 4.06, we have analyzed a number of fields in the halo. They are not subject to uncertainties due to dust, and we feel now we have a very robust calibration for NGC 4258. I'll mention also.
What about the Zhang and Lee? They analyze the outer fields as well and get minus 4.01.
Yeah, well, we've spent a lot more time looking at this in detail. The field that Zhang and Lee used, which was an earlier one that was analyzed by Major et al. As you can see, it's still fairly close in. And so we've analyzed fields that are much farther out. And when we look in detail, there's still some, we believe, reddening that affects the, and possible discontamination that affects the inner part of that field. But we've spent an enormous time analyzing the 4258 results. Those are going to come out very shortly, and we're confident that we have a very robust measurement of the distance to this galaxy. But that inner field sitting in the disk, it's like a classic. This is where you do not do the TRGB method for the reasons that Rachel, I think, very nicely outlined. I'll also say that we have calibration coming from galactic globular clusters, and that also is in very good agreement with 4258 and the LMC. But let me say a word to the slide that I put together, because this is a talk, a meeting that is assessing the uncertainties in the Hubble constant. And I think one of the things, so what I've done is to put together a partial list of systematics for various methods. And they're color coded, so you can see the smiley face and the unhappy face. And so they go from red to orange to yellow to green. And I think, you know, a reminder to all of us that, of course, this is a partial list, and what may be the worst systematics are the ones that we don't even know about. And certainly in the history of the distance scale, that's come back to bite us. And so Jeremy, I believe, will talk about the key project. We had a lot easier time in the key project where we were going from factor of 2 to 10%, because the systematics really were simple to identify and to quantify, and to eliminate in some cases and minimize in others. But if we look, for example, so the tip of the red giant branch, if we measure in the halo, the reddening is small. It's not a large systematic. the metallicity is low, we can calibrate the effect. Where I think, real difficulties in my view are the small number of calibrators. This is true for Cepheids and the tip of the red giant branch. We're stuck with a local universe that just doesn't have very many independent ways of getting at the 0 point. And the numbers of galaxies we can apply the method to that say we can step out to type 1a supernovae. And right now the comparable numbers in tip of the red giant branch and Cepheids. Crowding is not an issue in the halo. And I think it is important for methods that we have some sort of physical basis, not simply an empirical calibration. And the Cepheids, as Adam's pointed out, we've studied Cepheids now for a century, and they are well understood in certainly a level of a few percent, but 1% is a lot harder. And so multi-wavelength data or using the Wesenheit function that Barry Madore came up with in 1982 allows you to correct for reddening. Metallicity for the Cepheids, however, that's still something that's not well understood. There's no direct measurement of metallicity of the Cepheids. We use a proxy. The 0 point, as I've described for tip of the red giant branch, it's a similar kind of issue. The numbers of galaxies is increasing, but again, we're talking about 1%. That's a tall order. I will still put an orange in crowding. I think Adam has argued that that's now a dead horse, but the crowding tests that he has described were done for 20 megaparsecs most distant, and most of the galaxies in the sample are more distant than that, and the new sample will be even more distant yet. So certainly if we're going to talk about 1%, I think there's more work to do.
Glad you weren't a referee.
Well, I don't want to dwell on these, but you can see that numbers of red and orange for the other methods, they haven't been scrutinized for systematics in the same way as Cepheids and tip of the red giant branch yet. And I think if we are looking at things like Tully-Fisher relation and asking why do they have larger Hubble constants, they also have much larger scatter than supernovae. It's at least a factor of 4 higher, even in the infrared. And disentangling baryons and dark matter and understanding how the star formation evolutionary effects occur in Tully-Fisher relation. I think, again, if we're talking about 1%, we have a ways to go. So a point I'll like to make is that there are no all green methods. There's a lot of work I think we need to do to understand what the systematics are. And I think in terms of the calibration, masers are wonderful. It's a method that has a physical basis, but there's exactly one galaxy in the local universe that this method can be applied to, a geometric measurement. And understanding systematics there with a sample of 1 is pretty difficult. Things will improve with Gaia. The detached eclipsing binaries are giving a nice independent measurement, geometric distance calibration. But I'll stop by saying that I think 1% is a really worthwhile goal. We really want to try and achieve that, but we do need to distinguish systematic from statistical uncertainties. And I don't think we can be too confident that we've eliminated the systematic uncertainties, despite what I would say is actually rather remarkable progress, recent progress on the distance scale. So I think the CMB results are a challenge to astrophysics, and we need to remember that 1% for astrophysics is an enormously challenging task.
Thanks a lot, Wendy, for these insights. I just would like to mention that we have 3 minutes left to go in this panel, and Jeremy hasn't yet had a chance to speak, so I would like to give him an opportunity to add some things.
You can go directly to the one slide that you edited for me, Dragon. Good morning, everyone. It's Tuesday where I am, and so I'm speaking to you in this one slide from the future. And I think I'm trying to take a long-term view of where how we can improve the distance ladder in the next decade. Taking the first of these goals, I think the supernova goal as a standard candle is to learn enough about thermonuclear supernovae that for some of them we can find relative distances for any pair of them that are good to 1%. And Adam has already hinted that that's the way he's going with the supernova standard candles. Then we have a goal for nearby galaxies, which we currently distance using Cepheids and TRGB and a few other things. And really, this is just a part of matching the HR diagrams of galaxies in order to deduce their distances. So the goal would be to learn to match the HR diagrams of the nearest few hundred such hosts to 1% accuracy and distance. And of course, if you've got 100 galaxies, you've driven your random error down to become negligible. And the third goal is the geometric goal, because distance scale eventually has to be founded on geometry. And so the parallax goal is to measure the distances of several hundred stars relevant to HR diagram matching, or if you like, the PL relation of Cepheids. Anyway, things that are not invisible to us in our own galaxy to 1% accuracy. And I'm thinking that particularly two of these goals, we may be, by the end of the decade, be handing these over to machine learning, or at least be greatly influenced by machine learning to achieve the goals. If all of these goals can be met, then we would have knowledge of H0 to a distance modulus measured in millimagnitudes, and we'd be there amongst the accuracy achieved by the CMB. But of course, as we all know, the errors add up. And so if you miss any one of these goals, the error budget is such that it drags down the success of the other two contributions. But perhaps I'm saying optimistically from the future that all three goals are realizable. Thanks.
Thank you, everyone. Thank you very much. Richard, are we out of time?
Yes, in principle, this would conclude today's session. I don't really want to stifle discussion if you still would like to exchange a bit. I wanted to make sure that everyone certainly has a say among today's panelists. So maybe if other folks who were in the panel today had additional things to add, I would go 10 minutes over time. But then in the interest of those from joining from tomorrow, maybe let them go to bed at some point.
Yes, that sounds very good. Thank you. So sorry, I am still sharing my screen. Let's see. So would Rachel or Sylvia or Lloyd like to say a word? They gave talks. If not, we can go to impromptu comments.
I don't need to say anything.
Okay.
Yeah, I'll just say quickly, we've been looking into Adam's comment about the difference between Zhang and Lee and what I showed. And it's a little tricky, the table of the different values, because there's different ways to do the calibration. But if you use the, oh, sorry, I totally lost the screenshot. But the minus 4.01 number is the combination of the LMC and N4258, whereas I was just quoting N4258, which is like minus 4.04. I think Taylor put a number in. So I can send the screen grab with the table with the number that I was quoting. So I'm sorry for that. It's confusing. There's a lot of numbers on the table.
Well, I do see 4.02 in the Zhang and Lee paper, but you're right, the LMC one is more like 3.95. So I think the average of those is lower. But do you have some idea of how it gets to 4.06?
So Taylor's pointed out in the chat that Zhang and Lee get minus 4.04 if they use the read it all 2019 distance.
Yeah, I see 4.03, but that's pretty close to that. But there's still a few hundredths of a magnitude to 06.
Yeah, so I think we have a 0.01 difference in our actual tip measurement. And that's 1/100th of the difference. But the rest, I want to hold that off for the paper going deeper into that, because I don't think we have the time here.
Okay.
So this is a really good moment to notice something I've noticed in the beginning of this discussion, which is that observers are in the trenches. They are discussing 4.03 versus 4.04 because it matters. And lots of things are happening. And then theorists have been discussing, Evan there had a smiley face disappearing. There's a bunch of theoretical developments. You need greater than 1,000. Is there some middle ground where we can meet? Is there any places where observations and theories can interface at this point to better understand this?
Phenomenology, fitting curves.
Anyone else?
A question that did come up was also was one of the highly ranked questions is, what about flatness of the universe? So we talked about this a bit today, but it seems a little bit unfair as we're going so much into details in the various measurements that one number is 1.00 without an uncertainty, and it enters all of this. So,
but we do try curvature. It's not that we haven't tested it, and we would be delighted to discover, as Lloyd said, that the universe is not flat. It would be, it would be Nobel Prize for the Planck collaboration. We did that, and
how much does that inflate the uncertainty on H0 if you
so it was in my table, but so the main problem is that yes, the error bar I think inflates by a factor of 3, and it becomes really non-Gaussian and so on. But the problem is that the value shifts down rather than shifting up by a lot. Actually, I have it in front of me. It becomes H0 minus 2. So the curvature open actually shifts the. It's related to these curiosities that we have.
You're breaking up a little bit. So we couldn't quite.
Extra smooth thing of the high L peaks that we have in Planck.
Sylvia, you were.
Sorry.
We can't hear you, Sylvia, unfortunately.
You were all broken up. Sorry.
If you add in BAO.
Okay, sorry. Let me know if you can hear me well now.
Yes.
That was better.
Okay, I was just saying that. So we look at curvature. Curvature is related to some other issues in Planck that we mentioned, and it's at level of 2 to 3 sigma, and leaving that open does not solve the H0 tension. So if there is something there, maybe we don't claim that we discovered that the universe is not flat because adding BAO data and CMB lensing essentially brings you back to flatness. So we don't see consistency across different data sets for evidence for non-flatness, and for the H0 tension in particular, it doesn't help at all. The tension becomes worse in a non-flat universe.
That's a really interesting comment. The last one you made, yeah.
I think another factor besides H0 people should be sort of paying attention to is measures of omega matter done locally in the late universe versus the early universe. I mean, if there is something going on, the relationship between H0 and omega matter is so close, it would be really interesting. I know it's harder, but if we see any hints in that direction.
Could I ask Dragon a question?
Sure.
Tom Shanks here.
Sure.
Dragon, in your slide, why is it more reasonable to look for extensions on the basis of H0 tension to lambda CDM rather than look for extensions on the basis of underdensity in the local universe?
They may be one and the same, depends. You need to extend the model. Now your model will presumably be allowing for, that's one thing it may be doing, allowing for more underdensities. But you need to extend the model. It won't be lambda CDM anymore. I don't know what the name is, but in vanilla lambda CDM doesn't allow it. Now, which extension you go to, it's up to the people, you know.
Because the measurements for underdensity are just galaxy counts and seem very simple compared to CMB or distance scale at large distances.
But yeah, that's arguable. But even if they are, yeah, it's a good thing to do. It's just, no, I'm not saying it's not a good thing to pursue. I'm just saying that lambda CDM would never produce such an underdensity to explain this lambda CDM theory. Now, extended theory may, I don't know that. But let's see, there was, Richard, unless if you were going for questions, there was one top ranked question.
Could I just respond to that also, which is that, you know, you can, if you're in the, so we have the, you know, supernovae out to z=1. We have supernovae where there's, you know, precise BOS BAO measurements. And I mean, if you can think of the Cepheids as calibrating these supernovae, then you've totally bypassed the very low redshift Hubble flow, and you skirt any issues of what a void might do. And basically you can calibrate what's happening out at z=0.5 with the supernovae, tie that to the BAO scale, and we still have and we still have a problem. Right?
If you're talking about a large void, 150 megaparsecs, and you allow the cosmology to vary even a little bit, omega m 0.31, 0.32, you can do quite a lot of damage to the H0 issue. You don't get the whole thing, but a few percent. You're only looking for 9% anyway.
Z=0.5 is a lot, lot beyond 150 megaparsecs.
Okay, we are about 10 minutes over time now. As Dragan suggested, I would like to pick up the top ranked question to the panel that was on Slido. It comes from Thomas Müller at the University of Southampton. And the question is, should we start looking for new independent measurements of H0, or should we focus on reducing and understanding the uncertainties?
All of the above. I mean, new ones are unlikely to materialize and suddenly be the kind of precision we're looking for. They usually, when they're new and they show up, they're usually sort of 10%, which is nice, but it's not going to really check where we are right now. But they're nice. And, if you get started now, maybe in the future they will improve. And I also think that, we should be improving things to 1%. I don't think we have limited bandwidth to do both those.
Maybe one last comment on uncertainties. It's true that the individual systematic problems like systematic issues like crowding or individual uncertainty terms are not the main cause of the whole tension, but I think it's possible that together they might ease it. So it's I think it's still important to scrutinize, as also was mentioned in the last paper of Adam last month, to scrutinize all aspects of the problem.
Great. Thanks very much, everybody, for participating and for being on this panel. This was a really wonderful discussion. I'm really sorry that we have to end it here. But actually, rather than ending it, I would like to move it to Slack. So we have the Slack workspace that's going on the whole week. I encourage you all to please go on Slack. There's a channel for hashtag discussions where you can keep discussing things. If things come up that elsewhere fit in to the meeting during the rest of the week, we can pick it up again, possibly there. I also would like to ask all of today's speakers to look at the listings on their respective Slido question pages, and then to go on Slack and send replies to these questions. Because we got many, many more questions that we were able to answer today. So Sherry, Antoine, I guess from our side, a big thank you to everyone who participated today. This was really wonderful. I hope you all enjoyed it, and I very much look forward to seeing everybody back again tomorrow. And maybe just as sort of the end of the day, we can all put on our video again and wave. Have a good day.
Thanks. Thanks, Richard.
Thank you, Richard.
Thank you so much, Richard.
Thank you.
Bye-bye.
Great. Thanks, y'all.